All right, so let's look at number one of the equilibrium end of year review. It's a KSP equilibrium problem. So no acids and bases here. We're talking about dissolving. So it's how well does calcium hydroxide dissolve. So first let's write the reaction for what the dissolving of this looks like. So here it is, and the things you want to look for is remember that this is a solid, so it's not going to show up in our equilibrium expression at all. And it does not react with water, it's just dissolving in water. So dissolving is the dissociation of the ions. So the other thing to check is make sure you put charges and make sure that you remember to balance it so that we have a good starting point. And if we get stuck at any point along the way, we might consider an ice table. That's helpful. And of course, in part A, they want us to draw an equilibrium expression. So let's do that. Remember, products over reactants, but we're not going to put in the reactants because they're solids. So here we go. KSP equals, and you remember that KSPs are always concentrations because we're talking about how things dissolve in water. So you want to make sure that you use brackets. That's really important. And you can see the one thing I forgot here, which is also don't forget to put the 2 up here because there were 2 hydroxides. And that's our good expression. So part A, done. Now part B, they want to know what mass of calcium hydroxide is in 500 milliliters of a saturated solution. So you remember there's 2 ways that we tend to approach these problems. One is we figure out how well something dissolves and we look at the concentrations of the ions at equilibrium and then we can just plug them in and calculate KSP. But in this case we know KSP, so we're going to plug in KSP and we're going to be solving for these concentrations of ions. So that's what we're after. So I'm going to plug in this value and I'm going to solve for these. And I'm going to make a quick reminder here in just a second after I plug in the value. Alright, so the thing that I wanted to remind you of is, so when we plug in, here's the KSP, this is going to be x, this is going to be 2x squared. And a reminder of why this is 2x. I sort of wrote all this, so I can't do an ice table here, so I have to rewrite it over here. But you'll remember that in KSP expressions, well, there isn't really no concentration of this thing in the beginning because it's a solid, but the amount of it that's going to get consumed is some value x, and it doesn't really matter what it is at equilibrium because it doesn't show up in the equilibrium expression. These ions start at 0 before this thing is dissolved. This one goes up by x, and so you'll have some x amount at equilibrium. And this goes up by 2x, and you'll have some 2x amount at equilibrium. And of course, those are the equilibrium concentrations, so I plugged those into the equilibrium expression right there. So that's why it's 2x. And the thing to remember is that you always need to check that 2 here impacts not only the change, but also the coefficient in the equilibrium expression. From this point, I'm going to solve for x. So after doing the algebra, I get 0.01112 molar. So that is our amount of calcium hydroxide that dissolves in molarity. And remember, it's always a little weird to talk about solids in terms of molarity, but that's how many moles per liter dissolved. So since it's how many moles per liter dissolved, all we have to do is convert that to grams. So we have 0.01112 moles per liter. And then we need to convert the grams to liters, or the moles to grams. So 1 mole is equal to, and I got to add up the molar mass, and I get 74.1 grams for the molar mass. And if I calculated that, that of course would give me how many grams per liter I've got. And of course, in the end, I don't have a liter, I have 500 milliliters. So I want to multiply it times 0.5 liters. So let's see, my liters cancel, my moles cancel, and that will give me how many grams that I've got. So, I mean, you could do it one of 2 ways. You could stop, after the 74.1 and then realize that's how many grams dissolved per liter, and since you have half a liter, you could just cut that value in half. Or you could do the unit tracking technique that I just did. And so I get 0.411996 grams. And then I want to think about sig figs. There is actually, technically, 500 milliliters only has 1 sig fig, so, we could cut it down to 1 sig fig. Our KSP value had 2, but this measurement, so I guess they're saying about 500, so I might say 0.4 grams for my final answer. let's look at part C. Part C wants to know what is the pH of the solution. Well, we've already figured out most of it, which is not only do we know how much dissolves, since we know the value of X and what its concentration is, to figure out the pH, of course, all we've got to do is pH is going to relate to the concentration of hydroxide at equilibrium. So since we know this is 0.0112 and that's the concentration of OH, we just have to convert OH concentration to H plus and then to pH. So here I've taken my concentration of hydroxide, done the negative log of it, and my pOH is 1.9538, and then the pH, of course, comes from the fact that the two of them add up to 14, and so therefore my pH is going to equal 12.046. Let's think a little bit about sig figs. It came from all the other stuff, and so we talked in the previous one. Although actually we didn't use this because we were just figuring out the concentration. So I think we're going to go based on this guy because that was what we used initially to figure out what X was. So that had 2 sig figs. So we need to report our pH to 2 sig figs. Remember that the ones before the decimal and pH are not significant. So to 2 sig figs it would be 12.05 with these two being significant. Well, let's look at part D. They say if 1 mole of hydroxide is added to the solution in part B, what will be the resulting calcium concentration? Assume that the volume of the solution does not change. So there are two things we have to remember. Because this is a precipitated solution, the concentrations of these two will be determined based on KSP. So essentially what we're going to do here is plug in our KSP value, plug in our concentration of hydroxide, and then we can solve for calcium, because calcium will be determined by the concentration, because the two have to multiply together to be KSP. So our first step is figure out what is our concentration of hydroxide in the solution at the moment, then we'll plug it in and solve it. Well, we have a few things to consider. One is that, you remember when we went through our whole table over here and figured this all out, well, we did know the concentration of hydroxide because we knew that X was equal to 0.01112 molar, and so 2X, which is the concentration of hydroxide at that moment, was equal to 0.02224 molar, and that was our starting concentration. Then we were adding 1 mole of solid hydroxide to it. They said the volume doesn't change. The volume is still 500 milliliters. So I'm going to figure out how many moles I've got here in this first part, add the 1 mole to it, and then divide it back by that volume and figure out what the concentration is. So if I take my concentration of hydroxide, multiply it times my volume, that'll give me my moles. So I do have 0.0112 moles of hydroxide in the solution before we started. So now my total moles of hydroxide, let me go back a step there, is going to be 1 mole plus my 0.01112 moles. So the total number of moles that I have at that moment are 1.01112. So we're adding a lot of hydroxide to it. So my new concentration of hydroxide, which I'm going to put right in there, is going to be 1.01112 moles divided by my 0.5 liters, because the volume didn't change. They said it didn't. So I divided my mole amount by my liters. I got my concentration of hydroxide, plugged it in right there, remember to square it, and solve for my concentration of calcium, which this is the value that I got. So I'm just going to reiterate that I know that X is the concentration of calcium. And think about sig figs a little bit. You know, we've been saying 2 sig figs all along. The only thing that's new is we added in this 1 mole. So the 1 mole, when we're adding, you remember that that we care about the last significant digit, which I think is right there. This is much further. So in our answer here, it's really right there that's the last significant digit. So we're still, I think, at 2 significant digits. So 1.3 times 10 to the minus 6th molar that's a 6, is what I think our concentration is for calcium.